First, we'll observe an animation of a rear-end collision as it appears without high-speed photography. Here it is again. Whiplash injuries take place very quickly, as you can see. The whole collision from beginning to end takes place in about 0.2 of a second, while all of the occupant motion takes only half of that time, about 1/10 of a second, or in a blink of an eye. Obviously, we'll need to slow this motion down if we are to understand what happens during a low-speed crash. We're able to do this as we have data from dozens of test collisions that have used human volunteers in low-speed crashes. These test collisions were carefully planned, and all of the occupant motions were collected via acceleration measuring devices and were photographed at speeds of 500 frames per second. This sophisticated technology allows us to observe the occupant motions during a crash in great detail. So now let's slow this collision down from 0.2 of a second to about 4 seconds. Let's now analyze this crash step by step. At the moment before the collision, our occupant is sitting upright in her seat, looking straight ahead. As the target vehicle is struck, it begins to move forward. Since the car seat is bolted to the target vehicle, it moves with the car. As we saw earlier, all objects with mass also have inertia, and the occupant's body is no exception. Since the occupant has inertia, her body is going to stay in the same position until acted upon by some outside force. In this case, the car seat back. Eventually, the car seat moves so far forward that the seat cushion is completely compressed, and the seat back begins to exert force on the occupant's lower back, and the occupant's lower back begins to move forward. Because the seat back is not perfectly vertical, the occupant's body ramps up the incline as shown here. The seat back is bending backwards at this point as it meets the resistance of the occupant. The occupant's upper back starts out farther from the car seat and moves forward later than the lower back. As the car seat reaches its greatest angle backwards, the upper torso is fully accelerated forwards with the car seat. The occupant's head, however, has no portion of the car to accelerate it forward, since this seat, like 80% of cars on the road today, does not have a proper head restraint. And since the head has inertia, it remains in the same position as it was before the impact. But the torso is moving forward rapidly. Eventually, as we can see here, the lower neck begins to pull the head forward, causing the head to rotate backwards quickly over the top of the car seat. At this point, there is a dramatic difference in how the torso and the neck are moving in relation to one another. As we can see in this graph from a crash test of 5 miles per hour, the torso accelerates much earlier than the head. In fact, the torso has mostly stopped accelerating by the time that the head reaches its peak acceleration here. Just at the moment where the head has reached its point of greatest extension, we see that the car seat begins to spring forward and move to a more upright position. Because the torso is now moving with the seat back, the spring action of the seat pulls rapidly on the lower neck, causing the head to rebound forward ahead of the torso. This results in very high peak head accelerations, as shown in this graph. As we can see, peak head accelerations increase dramatically at higher delta V's. A difference of just 1 mile per hour in delta V between 4 miles per hour and 5 miles per hour results in peak head accelerations that double. High-speed film footage was collected first in the 1950s, and scientists thought that these test collisions had found the answer to how people could be injured during a rear-end collision. The researchers saw the rapid backward motion of the spine, known as extension, and concluded that the injury was caused by hyperextension. That is, the spine extended too far back, causing injury to the joints of the spine. This hypothesis was supported by other researchers who found damage to the spine of cadavers that was consistent with this mechanism of injury. Other researchers, however, were skeptical of this theory, especially when it was applied to people who had been injured in low-speed collisions or accidents under 10 miles per hour. These skeptical researchers then measured the amount of extension that occupants experienced during test collisions and found that in low-speed crashes, the head did not extend beyond the normal range of motion of the spine. The engineers concluded that because hyperextension did not occur, injury was impossible in low-speed crashes. Another group of engineers and physicians, however, had become interested in a new line of study. These scientists realized that the occupant motion during a rear-end collision is much more complex than it seems. The complexity of a low-speed collision is evident in this chart. This data was taken from a test collision of 5 miles per hour. The first object to accelerate is the car itself, then the lower back, followed by the occupant's torso. The last thing to begin moving is the occupant's head, since the inertia of the head keeps it in place until it is moved by the torso in the car seat. Early on in whiplash research, engineers focused almost exclusively on the x-acceleration of the occupant's head. X-acceleration is that which occurs in the front-back direction, or the horizontal plane. Later, other researchers noticed that there was a degree of z-acceleration, or in the vertical plane, when the occupant's body ramped up the car seat, but they assumed that this was unimportant.